Hi folks, Chris McClure. In this video we are going to follow up from our discussion of testing hypotheses about any sort of proportion by talking particularly about the proportion. Now we already did something like this in section 8.2, so we're going to do a little bit more, but this time it'll be a two-till test instead of just a one-till test. So we're going to actually make this a short video because you've already seen a lot of this. And if you are missing something, if you don't understand regarding the basics of hypothesis testing, go back and review what we discussed in section 8.2. Let's go ahead and read this. In this section, we're going to talk about complete procedures for testing a hypothesis, aka claim, about a population proportion. We'll take a look at the p-value method as well as the traditional critical value method in deciding whether to reject or not reject the null hypothesis. We'll look briefly at the confidence interval method, even though that plays a lesser role in hypothesis testing, but it could be used with some precautions. Okay. Now, as I mentioned before, regarding proportions, when we are testing claims about proportions, by all rights, we really should be using the binomial distribution. But when you have a large sample size, it's better and easier just to use a normal approximation to the binomial. And that'll give you a very, very good approximation. And the results are virtually identical. But if you want an exact method, well, I'll show you briefly at the very end of this section how you can use the binomial exact method in part 2. Now for part 1, we're just focusing on using the normal approximation. All right. Now here's the cast of characters. N is the sample size. P hat is the number of successes, x over n. You've seen this before. P here is the population proportion parameter. Q is 1 minus P. These right here are the same requirements that we needed, for a normal approximation of the binomial. You've seen this before, so I'm going to move on. Our test statistic is z. You've seen this from the previous section. P hat minus P over the square root of PQ over N. All right, I'm going to show you how to look up your p-value and your critical values. Don't confuse p-value with proportion p. We've already talked about that. P-value method, you could either use your graphing calculator or the z-table to look up your p-values. Critical value method, typically we just want to use a table to look those up. I'll show you. In confidence interval, well, we've already had the discussion of how to calculate confidence interval of where you need your z critical value times that square root of PQ over N. Let's look at this caution real quick. I'm just going to read through this. When testing claims about a proportion, the traditional method and the p-value method are equivalent. They'll always give you the same result based on the claimed proportion p. But the rest of this basically tells you if you intend to use a confidence interval to test a claim about a parameter, in this case p, then be very careful, because the confidence interval is centered on p hat. Okay, so it's generally going to be an okay, I have lukewarm confidence in it, but if the consequences of getting it wrong are rather severe, I would use the more traditional value or the methodologies of the p-value method or the critical value method. Okay, so here's the example that we're going to use to see how to do hypothesis testing to test claims about proportion. Based on information from National Cybersecurity Alliance, 93% of computer owners believe that they have antivirus programs installed on their computers. We're going to use that 93% as our null hypothesis. Now, we've gone out, taken a sample of 400 computers from the population. And for each of these computers, we scanned and decided whether it did or did not have antivirus software on it. And it turned out that 380 of the 400 computers that we examined actually did have antivirus software. And if you take 380 divided by 400, you get 95%. Now, 95% is actually greater than the 93% that was claimed up here. And is this difference, is 95 versus 93% enough of a difference to be significant? Now, before we go any further, let's check to see whether we can use a normal approximation of the binomial distribution. And these are the three things that we have to check. First of all, do we have a large enough sample size? 400? Yes. And we have a binomial experiment, as we see here, for requirement number 2. Requirement number 3, NP and NQ both have to be at least 5. And N is 400, P is 0.93, 400 times 0.93 is 372, so that's greater than 5. And NQ likewise is also greater than 5. So yes, we can use the normal approximation to the binomial. So we can use the Z test statistic. Now, we are going to write our null hypothesis is that the proportion of computers with antivirus software is 0.93, 93%. And because we're not sure whether the alternative should be greater than or less than, we'll just simply state that it's not equal to. Okay? So this will turn out to be a two-tailed test. Now, using the p-value, I'm going to show you how to decide whether to reject or not reject that null hypothesis. Now, we were not told tests that claim at any particular value or level of significance, so we will, by default, select alpha to be equal to 0.05. And of course, we will use this calculation right here for our test statistic. You've seen this before. P hat is 380 over 400 minus the claimed value for P from the null hypothesis, that's 0.93, divided by the square root of 0.93 times 0.07. Remember, P and Q are, they have to add up to 1, divided by the sample size 400. So evaluate this whole thing, you should get 1.57. So our result of 0.95 was 1.57 standard deviations above the mean. Is that unusual? No. I'll just tell you right now, no. It's, Now, this was actually a two-tailed test. In order for us to calculate a p-value, though, what we need to do is take a look at where 1.57 is, was 1.57 standard deviation to the right of 0 on the standard normal distribution. And then the area under the curve to the right, it works out to be 0.0582. Where did we get that? Well, let's pull out our Z table. Do I still have it open? Yep, here it is. Now, our Z value was 1.57. To find the area to the right of 1.57, I could just as well find the area to the left of negative 1.57. So let's go to our Z table. There's our Z table. And let's go to the first page, and let's look up the Z score of negative 1.57. There we go, negative 1.57. Here's negative 1.5, and we'll come over to the 0.07 column. This one right here. And that probability is 0.0582. But here's the thing, for calculating our p-value, we need to double that for a two-tailed test. So 2 times 0.0582 is 0.1164. Okay? And because that value of the p-value is greater than the alpha level of 0.05, we would fail to reject the null hypothesis. We would reject it if the p-value was less than or equal to 0.05. But as it is, we fail to reject. What does that mean? Well, the null hypothesis was that 93% of computers have that antivirus software. We fail to reject that, and we see no reason to believe that that proportion of computers is any other than 93%. Okay? Now, if you want to do critical value, then you take alpha, which is 0.05, divide that in half, you get 0.025. You put 0.025 in each of the two tails. What is the z critical value which separates off those two tails? Let's go back to your z table here, and let's look at the z value. So you have 0.025 in the left tail. 0.025 is right here in the main body of the z table, and the corresponding z value is negative 1.96. And likewise, because of symmetries, positive 1.96 would be associated with the right tail, with 0.025 under the curve to the right. So if your z test statistic was less than or equal to negative 1.96 or greater than 1.96, we would reject the null hypothesis, because that would land us in the so-called rejection region. But as it is for our problem, our z test statistic was 1.57. Where did that come from? From this calculation here. And because our z test statistic value was not at least as extreme as our critical values, we failed to reject the null hypothesis. And again, come to the same conclusion, that we don't have enough evidence to believe that the proportion is anything other than 93% of computers that have antivirus software on there. Now, if it turned out that we had already calculated a confidence interval, well, look, we had already done that right here. This was from a previous section, section 7.2. And notice that our null hypothesis says that p is equal to 0.93, and that is actually within that confidence interval. And if your hypothesized value for p is within the confidence interval, then you would not reject the null hypothesis. This is a 95% confidence interval. But if your hypothesized value for your parameter was outside of the interval, then you would have reason to reject the null hypothesis. Okay? Now, regarding the exact methods, I'm just going to cover this real briefly. We would use the binomial distribution. So, left-tailed test, probability of getting X or fewer successes from n trials. Right-tailed test, the p-value is the probability of getting X or more successes among n trials. And two-tailed test, if p hat turned out to be greater than p, then the p-value is twice the probability of getting X or more successes. And now, this little typo here, this should be if p hat is less than p, then the p-value is twice the probability of getting X or fewer successes. Okay. Now we're just going to do a real quick example. You can look at the details in the textbook if you want. And I think that you might have one or two problems in the homework as well. All right, so we're going to take a look at a real small sample here. Suppose that we've got 10 randomly selected couples who are treated with a gender-selected method, a gender selection method, kind of like the XORT method, in which you are more likely to conceive of one gender or the other. Now, suppose that of the 10 randomly selected couples who underwent treatment, that 9 of those conceptions ended up with girls. Is that a big enough departure from 0.5 or 50% to convince us that this method is not ineffective? In fact, we're going to use a 0.05 level of significance to test the claim that with this method, the probability of a baby being a girl is greater than 0.75. This company, who has come up with this method, is claiming that it's better than 75% chance that your conception will end up with a girl, that you will have a girl when you're trying to conceive. So let's test that claim. Now, I know this is a rather small sample, but you can extend these results to a sample of any size. Okay? So here's how we'll do the hypothesis test. Null hypothesis. Remember, the null hypothesis is always a statement about equality for the population parameter. In this case, P is going to be set equal to 0.75 because that was the claimed cutoff value, because we're being told by this company that their success rate is greater than 0.75. And because we hear the word greater or the phrase greater than, our alternative hypothesis will be that P is greater than 0.75. Now, this is the right tail test, so all we need to do is calculate the probability of getting 9 or more successes out of 10 attempts. And as we could see from this printout from the software called StatDisk, now here we've got this printout that shows out of 10 successes what the probability for each, there's 10 trials, 10 trials. And this second column will calculate the probability of getting this number of successes. So, for example, the probability of getting 5 successes out of 10 attempts, or 10 trials, 5 out of 10, that probability is 0.0583992. You know how to calculate binomial probabilities. These are just binomial probability. The probability of getting 8 out of 10 successes, another binomial probability. All of these are binomial. That is 0.2815676. Now, over here in the third column, we have the probability of getting X or fewer. Last column, probability of getting X or greater. Now, we're interested in calculating the probability of getting at least 9 successes, because after all, you look at the results of our experiment, we had 9 girls out of 10 babies. So the probability of getting a result at least as extreme as we did would be the probability of getting 9 or more babies that are girls out of 10 babies. And notice that probability of getting 9 or greater is 0.2440252. That's going to be our p-value, which is a rather high p-value compared to the typical alpha level of 0.05. So we would fail to reject the null hypothesis. And we would conclude that there's not enough evidence to support the claim that the rate of success of girls is any more than 0.75. Okay? Don't worry, you'll have a chance in future sections to see where you get to reject the null hypothesis, as we shall see in upcoming videos. All right. By the way, and I'm going to send another email out about this, is I'm going to be going on vacation starting tomorrow, actually late tonight, and I'm going to be out of the loop. You won't be able to reach me, except maybe by email tomorrow or Thursday morning by email. But I promised my wife that I will leave work behind for about a week. I'm going to be on a cruise, be gone until Monday morning, and then I'll be at least connected with email again until I get home. Then I'll be back to work on Tuesday or maybe Wednesday. Okay, so that's it for now. I'll try to record videos for sections, um, well, for the rest of Chapter 8 this evening before I go. All right, have a good evening, and we'll see you next time.